In this video, we're going to talk about how to find the derivative of a logarithm, and we'll explore that a little bit, and then we'll do some more practice with inverse trig functions in the chain rule with them. So we know that the derivative of e to the x is e to the x. That's our favorite derivative. We know that the derivative of e to the u is e to the u times du. So that's our chain rule as applied to an exponential. So we also know that e to the natural log of x is equal to x because an exponential base Euler's number and a logarithm base Euler's number are inverses of each other, and so they cancel each other out. So we can think of now, this is kind of an interesting use of our chain rule. We're going to think of that as taking the derivative of e to the u, where the u is going to be that natural log x, and that's the derivative we don't know. So from here, we're going to get that same exponential, e to the u, times, and we don't know the derivative of natural log x. That's what we're trying to find out, and so we're going to try to resolve that. Now on the other side, the derivative of x is just 1. So now this is what we're looking at. Now we also know that this e to the natural log x we said was just x. So that's really saying that x times the derivative of natural log of x is equal to 1. So if we divide that x to the other side, we find the derivative of natural log of x is 1 over x. How about that? Isn't that interesting? So we can also now do the derivative of chain rules with a logarithm. So the derivative of, say, natural log of 5x is going to be, we're going to call this du over u, or you can think of it as 1 over u times du, either way. So that means we're going to get 1 over u, we'll get that 5x, and then times the derivative of 5x, which is at 5, and isn't that interesting that it turns out to be exactly the same thing? Now, if we do the derivative of, say, the natural log of x squared, here's two ways of doing that. We could do this as du over the, or du 2x over the u, the x squared, which we could simplify and call 2 over x. What I'm going to encourage you to do is, especially when these get really complicated, is use our properties of logarithms first. Remember, the natural log of x squared is, you can bring that exponent out in front and call it 2 natural log x. And so the derivative of a constant times a function is the constant times the derivative of the function. And there's another way to get to the derivative of natural log of x squared is 2 over x. If you had something like the derivative of natural log of x squared plus 5, now there's no clever rules for logarithms, so we would just get 1 over u and then du. Now we can also find the derivatives of logarithms with other bases. So suppose we have a common logarithm, a logarithm base 10. Now you're going to see why we like natural logs so much in calculus. We don't know how to differentiate this, so we have to do a change of base. So if you remember change of base, there's an unwritten 10 there. We're going to convert this to its exponential. 10 to the y equals x. And then from there, we're going to now take the natural log of both sides. So that's going to take us to here. We can use our property of logarithms and bring that y out in front to get to here. Now we can divide that natural log 10 to the other side. So the shortcut is, remember, y was our log of x. So to change a logarithm to a different base, and in calculus, we're always going to want to change it to a natural logarithm, because that's the derivative that we know, and it should have been a natural log 10. I dropped that ball. So now, we're always going to try to convert it to a natural log. So now we can take the derivative of this, because remember, this natural log 10 is just a constant that's multiplying that natural log of x, and so we get 1 over x natural log 10. So to summarize, if we had, say, f of x is a logarithm base 5 of x, we would convert that to a natural log x over natural log of 5. Then we could take its derivative by taking the 1 over natural log 5, that constant, times the derivative of natural log x, and to avoid confusion, we'll write that x in front of the logarithm. Okay, let's go to a new panel and let's do some chain rule derivatives with inverse trig functions. Chain rule with inverse trig functions. Make sure we get the hang of this, because there'll be some algebra involved in some of this. And I'm going to try to mix up the notation. Sometimes I'm going to use the inverse function notation like this, and sometimes we'll use the arc sine notation. So our derivative here is going to be, we're going to get du over the square root of 1 minus u squared. So du is the derivative of x cubed, and 1 minus x squared is 1 minus x cubed squared, which is going to be 1 minus x to the 6th. Okay, let's do the derivative of the arc sine of the cube root of x. So we're going to get du. Now that's the derivative of x to the 1/3. So that's going to be 1/3 x to the negative 2/3 over the square root of 1 minus, and that's going to become either the cube root of x squared or x to the 2/3. Either way, we can bring this negative exponent and the 3 down below. So maybe, I think I'm going to leave it just in fraction notation there. And I think I'm going to go back and be consistent and call that 1 over x to the 2/3 there. Okay, not very pretty, but that's what we got. Let's do the derivative of, say, an inverse tangent of, and I'll say 5 to the x. So this is going to be du over 1 plus u squared. Du is kind of messy. That's the same exponential times the natural log of 5 all over, whoops, no square root for an inverse tangent. It's going to be 1 plus 5 to the x squared. So you'll be expected here to simplify that. And of course, remember, when you raise a power to a power, you're going to multiply those exponents. So we'll get to 1 plus 5 to the 2x. Let's find the derivative of arc tangent of, and let's say maybe we've got here x over 3. Okay, this is going to be a little windy. Du, so we're thinking of this x over 3 as being 1/3 x. We don't want to use the quotient rule there. So du, the derivative of 1/3 x, is just 1/3. We're going to get 1 plus our x over 3 squared. So that's going to look like 1 plus x squared over 9. Now we don't want to leave fractions in fractions, so there's kind of two ways of doing this. I think the most efficient way is if we multiply top and bottom by the least common denominator, by the 9, then what we're going to get is the 9 times 1/3 will cancel, and we'll get 9 times 1 is 9, and the 9's will cancel with the x squared over 9, and we'll get to 3 over 9 plus x squared. Let's do the derivative of, let's say, d dx, and let's do arc secant of, and we'll say x over 5. Okay, so this, remember now, is going to be du over the absolute value of u times the square root of u squared minus 1. So again, du is going to be 1/5. We're going to get the absolute value of x over 5, the square root of x over 5 squared minus 1. So that's going to be our 1/5. We've got the absolute value of x over 5. We've got the square root of x squared over 25 minus 1. Here's where the algebra gets a little bit serious. So we want to, in this denominator, we're going to factor out. So I'm just going to look at, in the radical in the denominator, we're going to factor out 1/25. That'll leave us with x squared. Now when you factor out a 1/25, you're dividing this by 1/25, which is going to multiply it by the reciprocal. Or another way of thinking of it, when you distribute, 1/25 times x squared takes us back. 1/25 times 25 gets us back to 1. Now in this radical still, we're going to pull this outside as the square root of 1/25, which is 1/5. So this is now looking like, we're not done yet, but we can say that's 1/5. We've got the absolute value of x over 5, and we've now just pulled a 1/5 out of that radical. Now we can say we've got 1/5 over. Now this 1/5 that's in that absolute value, so the absolute value of x over 5 is the absolute value of 1/5 times the absolute value of x, which is just 1/5 times the absolute value of x, which is to say you can just pull that 1/5 out since it's positive. So you have the 1/5 from the absolute value. You've got another 1/5 that came outside the radical. You got the absolute value of x, and you got the absolute value of x squared minus 25. One of those 1/5s will cancel. This divide by 1/5 in the denominator will become a 5 in the numerator. We'll still have that absolute value of x, and we'll have the square root of x squared minus 25. Wow, that's pretty crazy. Let's go to a new panel and do a couple. So let's do the derivative of arc cosecant of e to the x. This one's kind of crazy. So remember, we're going to get a negative du over the absolute value of u times the square root of u squared minus 1. So the du is the derivative of e to the x. That's just e to the x. We have the absolute value of e to the x times the square root of e to the x squared minus 1. So let's see what we can do with this. Now, when we think hard about this, e to the x is never negative. So it doesn't need an absolute value. The absolute value of e to the x is the exact same as e to the x. In the radical, e to the x to the second, we multiply the exponents. That becomes e to the 2x. Now we're safe to cancel those e to the x's. So our simplified answer is kind of crazy because it doesn't really look like it came from a derivative of an arcsecant at all, because you don't see any absolute value in there. Interesting stuff. Now, here's a crazy one. There's going to be a lot of algebra here. We're going to take y equals the arcsine of x plus the x times the square root of 1 minus x squared, and we're going to try to find this derivative. So there's going to be a lot of calculus, and there's going to be a lot of algebra in this one. Now, the derivative of arcsine of x, that's just 1 over the square root of 1 minus x squared. Now, the next one is a product rule. So we have the first, which is x, times the derivative of the square root of 1 minus x squared, but that is a chain rule derivative. So we're going to have 1/2 times 1 minus x squared to the negative 1/2 times the derivative of the inside function, which is a negative 2x. So all that is the first times the derivative of the second, plus the second times the derivative of the first, which is just 1. Okay, let's see what we can do. We've got 1 over the square root of 1 minus x squared. Now here, this 1/2 and that 2 are going to cancel. The x times the negative x is going to be a negative x squared. The negative exponent is going to throw that into the denominator, and that's going to be the square root of 1 minus x squared. And then we still have a square root of 1 minus x squared. Well, let's see. How about if we get a common denominator? Since these two already have that same denominator, let's multiply this one, top and bottom, by that denominator and see where that leads us. So, it looks like we're getting 1 minus x squared. This is all going to have that same denominator, square root of 1 minus x squared. Now we multiply these two. Well, that just removes the radical and gives us a 1 minus x squared. So let's see, that looks like 1 plus 1 is 2 minus 2x squared all over the square root of 1 minus x squared. How about if we rationalize this? Not that we normally want to do this, but I see good things happening here. So if we do that, we're going to get, and while we do this, I think we can also factor a greatest common factor out of that. So that's going to be 2 times 1 minus x squared times that square root of 1 minus x squared. In the denominator, we're going to get 1 minus x squared. Can you believe it? Those are going to cancel, and we end up, after all of that, with 2 times the square root of 1 minus x squared. Pretty crazy stuff. Okay.